Hi Year 12 and welcome back to your distance learning lessons. Today we are going to be looking at the ideal gas law. Let's start as usual by doing our knowledge retrieval. So pause this video now and take 2 minutes to complete the following 3 questions. Right, let's have a look at the answers. Question 1 asks you what Boyle's law states. So if you remember back to last lesson, Boyle's law said that for a constant temperature, the pressure and volume of a gas are inversely proportional. Question 2 wants you to sketch a graph that shows Charles's law. So Charles's law was all about the idea that for a constant pressure, the volume of a gas is directly proportional to the absolute temperature. So we're going to have to plot our volume v temperature. So V on our y-axis and temperature, which I'm going to put in Kelvin, on our x-axis, and it's directly proportional, so we expect to see our straight line. And then our final question asks us how to convert between Celsius and Kelvin on the temperature scale. Well, to go between Celsius and Kelvin, we want to add 273, and to go from Kelvin to Celsius, we want to subtract 273. Okay, so today what we're going to start off with is looking at something called the combined pressure law. This is something that will not often come up in your exams, but may appear and is very useful for you to know. We're going to start by looking at the 3 laws that we learned last time. So, previously, we saw Boyle's law that said that essentially P multiplied by V, so pressure multiplied by volume, is equal to a constant. We also saw Charles's law that the volume divided by temperature is equal to another constant. And we saw our pressure law, which was pressure divided by a temperature is also equal to a constant. Now, if we were to combine these 3 equations, which you do not need to know how to do, we're going to end up with something that looks like this. So our P multiplied by V divided by T is going to be equal to a constant. Okay, so you don't need to know how to combine those 3 laws to get this one little thing here, but you do have to know that that's what it would roughly look like. And that is actually a really helpful law for us to understand, because essentially at this point we can be talking about 3 different things that will change the pressure, the volume and the temperature. And when we change those things, we can use our equation here to figure out an unknown value, because it's always going to be equal to a constant. So let's have a look at a quick example. Let's say that we have a gas that is at a pressure of 100 kilopascals. And it's in a box that has a volume of 1.2 meters cubed. And the temperature of that gas is at roughly 30 degrees C. So that's where our gas will start. Let's say that after some time has elapsed, we find out that our pressure has increased to 120 kilopascals, but the volume has decreased to 1.13. And we want to figure out what our new temperature would be in this instance. So we can use our combined pressure law to figure out what that constant might need to be. Let's put those numbers in and see what we can do. So we have our pressure, which is 100 times 10 to the 3 pascals, multiplied by our volume, which is 1.2, and that's going to be divided by our temperature. Now, you'll remember last time that we actually want our temperature to always be in Kelvin, and at the minute it's in degrees C. So we're going to have to add 273 to 30 to give us our new temperature, which gives us a temperature in Kelvin of 303 Kelvin. And that's going to be equal to a constant, which if we plug those numbers into our calculator, we find out that that constant is 396. Now that constant is going to help us a lot in situation number 2 as listed above, because it's obviously not going to change, it is constant. So looking at our new situation, so that's situation 1, if we look at our second situation, we can use our constant to figure out what our temperature is. So we'd end up with 120 times 10 to the 3 multiplied by 1.13 divided by temperature, and that's going to be equal to 396. Therefore, our temperature is going to be equal to 342.39 Kelvin, which if we minus 273 from, we get an answer of 69.39 degrees C. And you can see that that kind of makes sense. If we've increased the pressure by 20% but haven't decreased the volume by the same, i.e. there hasn't been a decrease of 20% in our volume, then something must have happened to the temperature to attribute to that increase in pressure. And the only thing that could have happened to get a higher pressure is that we've gotten a higher temperature, which you can see there. Now, this combined pressure law is not given to you in your exam on your data sheet, but it can come in quite useful in situations as seen in our little example there. What you are given, however, are these two separate ones, and we're going to talk about them in our next couple of slides, but I'll show you what you are given first. So you're given the following: PV equals nRT. That's one equation that you're given on your data sheet. You're also given the following: PV equals big N KT. So those are the two equations that you're given on your data sheet. Now you can see that roughly those two equations can be put into similar style of our combined pressure law. So even though you're not given that combined pressure law directly, you can always work it out from the two equations on your data sheet if you put it into a similar looking equation as seen here. And therefore, if you've got the same amount of stuff or same material in each situation, you can use the combined pressure law to help you solve questions. Just seen two important equations that are on your data sheet, but we haven't really spoken about what those equations mean yet. Now, before we actually even get onto that, what I want to have a look at is these two parts of that equation. Little n, which is the number of moles, and big N, which is the number of molecules. And I think it's really important that we break this down right now, because you not only will see this here, those of you who take chemistry will, I'm sure, have met these ideas as well. And on top of that, we're going to have to use these two numbers when it comes to looking at our radioactivity portion of A2. So it's really important that we get a good, strong grasp on number of moles and number of molecules before we move on to looking at these two equations that we've actually got here. So number of moles is what we're going to start off with, because these two things are kind of inextricably linked. Number of moles, little n, is a base SI unit and was basically coined by Avogadro. He's a really, really important person in what we're going to talk about for the next few minutes. Now, what he did was he looked at carbon-12, which, as we go through the A-level physics course, you'll realise is actually a really, really important element. So carbon-12 looks something like that, has 6 protons, 6 neutrons, and a mass number of 12. And essentially what Avogadro did was he worked out that in 12 grams of carbon-12, So in 12 grams of carbon-12, he established how many atoms were present in that 12 grams of carbon-12. Now, the reason he looked at 12 grams was because it has a mass number of 12. So he figured that going between 1 gram would be equal to the mass number of 1. Then carbon-12, to have a look at number of atoms, it would make sense for him to have a look at 12 grams of carbon-12. So he said essentially that 1 mole was equal to 12 grams. And after doing some pretty advanced chemistry, he figured out that actually in 1 mole of anything, of any substance ever, there is going to be a certain number of atoms in that 1 mole of anything. And that is what gets called the Avogadro constant, or Avogadro's number. We write that down. So Avogadro's number, Avogadro's constant, we give the symbol Na. And essentially that number is 6.02 times 10 to the 23 atoms. So in 1 mole of any substance in the universe, that's how many atoms are in that 1 mole of substance. Now, back to what we are talking about here. He said that in 12 grams, which is 1 mole of carbon, there is therefore 6.02 times 10 to the 23 atoms. Now, that's all fine and good, but most of the time in both physics and in chemistry, they're not just going to give you a nice simple question where you've been asked to deal with 1 mole of a substance. You'll normally get given a different amount or a different mass amount of a substance. So let's say now that we have 15 grams of carbon. So instead of having the 12 grams, the 1 mole of carbon, we've now got 15 grams. So we want to figure out essentially how many moles are in 15 grams. So we're going to have to divide 15 by 12, and that's going to give us 1.25 moles in 15 grams. Therefore, to find out how many atoms we've got in 1.25 mole of carbon-12, we can multiply through by Avogadro's number. So we get 1.25 times 6.02 times 10 to the 23, and we're going to end up with 7.525 times 10 to the 23 atoms are in 15 grams of carbon-12. So if you know what you're doing there, then we can essentially link together in a really important manner the number of moles versus the number of molecules and how they all link together. So, number of moles, little n, is going to be equal to number of moles divided by the molar mass. And the molar mass is essentially nothing more than the atomic mass. Okay, so this is a really, really important link between the number of moles versus the number of molecules that you can find out. So we're going to see how those two things link and why it's important as well. So, look now at something like carbon dioxide. Okay, so before we were looking at carbon-12, it's an atom. Now we're going to have a look at a molecule. So let's have a look at carbon dioxide. You know that for carbon dioxide, we've essentially got 1 atom of carbon-12 and we've got 2 atoms of oxygen-16. Okay, so that's what we're looking at in terms of our structure here. So 1 molecule of carbon dioxide is essentially got to be equal to a carbon-12 plus an oxygen-16 plus another oxygen-16. So you want to add those atomic mass numbers together and we'll get a molar mass of 12 plus 16 plus 16, which is equal to 44 grams. So 1 mole of CO2 is equal to 44 grams. So we could work out number of molecules by multiplying through by Avogadro's constant, but let's just skip straight forward to dealing with a different amount of carbon dioxide. So let's say we've got 100 grams of carbon dioxide. So if we've got 100 grams, we want to figure out how many moles of carbon dioxide we have. So we've got 100 over 44. That's going to give us 2.27 moles. And therefore the number of molecules, if we've got 2.27, we can multiply that through by Avogadro's constant. So 2.27 times by 6.02 times 10 to the 23 is going to give us 1.37 times 10 to the 24 molecules of CO2. Now, it's really important here that we're distinguishing between molecules and atoms, because remember, we're not dealing in atoms here, we're dealing exclusively in molecules. So again, we have to go back to how we've originally broken down our carbon dioxide. In 1 molecule of CO2, we have 1 carbon and we've got 2 oxygens. So that's the ratio that we have to work with this number here. So therefore, number of atoms wise, we'd have 1.37 times 10 to the 24 carbon atoms, but we've got 2 oxygen atoms making up our carbon dioxide molecule, so we're going to have 2 multiplied by 1.37 times 10 to the 24. That's going to give us 2.74 times 10 to the 24 oxygen atoms. And you could add those two together, the oxygen and the carbon atoms, to find out the total of number of atoms in 1 molecule of CO2. So that's why this is really, really important to distinguish between the number of moles and the number of molecules. If you're talking about atoms, so our carbon-12, just our oxygen, etc., then you can work out really quickly how many atoms exist by looking at the number of moles and the molar mass. But if you've got molecules, which more often than not you'll have to deal with at A-level physics and A-level chemistry, then you're going to have to work out the ratio between the molecules that you've got before you find the total number of atoms present. Okay, so jumping back a little bit then to our gas equations. We've seen already our constant or combined pressure equation, which was PV over T is equal to a constant. Sorry if you can hear that, that's just my cats going a bit mad running around the room because they've just had their tea. Okay, so we've got our combined pressure equation there. If we put in values for 1 mole of an ideal gas at room temperature and also within our Earth's atmospheric pressure, we can define something that we call our molar gas constant, which is R. Okay, so if we put in all of those values, then our constant ends up being something called the molar gas constant, which is R, and that gives us a number of 8.31 joules per Kelvin per mole. Okay, so that is something that is given to you on your data sheet, and it's going to come in really, really handy. Now, if we look at this side of our equation here, PV over T, as that increases or decreases, if there's more or less gas present, then essentially the more gas that you have, the more space it takes up. The amount of gas is measured in moles, which is why we've just spent so long looking at the number of moles, so little n, so that the constant in the equation above becomes n multiplied by R, where n is the number of moles of gas present. So essentially, we can rewrite our combined pressure equation to give something that looks like this. PV over T is equal to our number of moles multiplied by our molar gas constant. This equation here essentially gives us what we call the ideal gas equation for a number of moles, which is that PV is equal to nRT. This is the ideal gas equation. It's really, really important. It's on your data sheet, but let's go through what everything is here. So we've got our pressure, which is measured in pascals. We've got our volume, which is measured in meters cubed. Number of moles, so number of moles of gas. Our molar gas constant, which is 8.31 joules per Kelvin per mole. And we've got our temperature, which is measured in Kelvin. That equation works really well, actually, okay? So we're constantly talking about this ideal gas, which you will know because we've made all of these assumptions, doesn't really accurately sum up how gases actually behave in the real world. But a real gas actually does approximate to an ideal gas for gases at low pressures and fairly high temperatures, which is most of the time what we'll be talking about here, and also what actually really does happen in real world situations. So this is actually a really, really important gas to use, equation to use in both chemistry and physics. So we've already seen our ideal gas equation, PV equals nRT. But we also briefly saw that we have a different version of this equation that we need to think about, one that involves the letter K. K in physics is a really important constant known as the Boltzmann constant. It's really important, not just in this, but in many different aspects of physics. And it's going to be something that you're going to come across an awful lot. K is essentially equivalent to the molar gas constant R divided by Avogadro's number, Na. If you were to put those numbers in to our equation, you would end up with the Boltzmann constant being 1.38 times 10 to the minus 23 joules per Kelvin. You can think of it as essentially the gas constant for one molecule of gas whereas R is the gas constant for 1 mole of gas. So here is where you'll be looking at your molecules, and that's when this becomes important. So if we think about what links the number of molecules, the number of moles, and Avogadro's constant together, we can define an equation that we've kind of already seen, but in a slightly different format. That the number of molecules is equal to the number of moles multiplied by Avogadro's constant. And we also know that K is equal to R over NA. Therefore, we can kind of see that NK is equal to NR. If we rearrange equation number 1 to make Avogadro's number the subject of that equation, then we can see that NA is equal to N over little n. And if we substitute that rearranged equation into equation 2, then we will see that K is equal to R over NA, which is equal to R over N over little n, which gives us NR over N. Therefore, NR is equal to NK, which is what we've just seen here. So I'm just showing you how we derive that. If we substitute that into our ideal gas equation, so PV equals nRT, then we end up with the ideal gas equation for N molecules. So ideal gas equation for N molecules ends up being PV is equal to NKT. This time your pressure and your volume are exactly the same, so is your temperature, it's always measured in Kelvin, except this time we've got K, which is the Boltzmann constant, which is 1.38 times 10 to the minus 23 joules per Kelvin. And we've got big N, which is our number of molecules of gas. And that's it. Those are our two really important gas equations that describe ideal gases. And you will find both of those equations on your data sheet. Let's have a look at some examples of when to use these two equations. Example says, what is the volume occupied by exactly 1 mole of an ideal gas at room temperature, which is 20 degrees C, and atmospheric pressure 1 times 10 to the 5 pascals. So we're using our first ideal gas equation, PV equals nRT, because we're talking about 1 mole of gas. And I'm going to straight up rearrange that equation to have volume as the subject of my formula, because I know that that's what they're asking me to find when they ask me for the volume there. So V is equal to nRT all over pressure. And then I'm going to substitute the numbers that I need in. So I've got 1 mole. I've got my gas constant, which is 8.31. My temperature is 20 degrees, and I need to change that into Kelvin, so I need to add 273. So that is 293 Kelvin. And my pressure is 1 times 10 to the 5. So subbing those numbers in, I'm going to get that volume is equal to 1 times by 8.31 times by 293 over 1 times 10 to the 5. That's going to give me an answer of 0.0243, which I'm going to round to 3 sig figs because that's what matches the rest of my questions, which is going to be equal to 2.43 times 10 to the minus 2 meters cubed. The next example says that an ideal gas at 303 Kelvin and 1 times 10 to the 5 pascals occupies 23.2 litres. How many molecules of the gas are present? So this time they're asking for the number of molecules. So number of molecules means I'm going to have to use our other version of the ideal gas equation. So that's PV is equal to NKT. And again, it's asking for the number of molecules. So I'm going to straight away rearrange that equation to give me N as the subject of my formula. So N is going to be equal to PV over KT. Then I'm going to collect what numbers I need from my example. So the pressure is 1 times 10 to the 5 pascals. The volume is 23.2 litres, but we need that in meters cubed. So I know that 1 litre is the same as 1 times 10 to the minus 3 meters cubed. So that's going to be 23.2 times 10 to the minus 3 meters cubed. K is the Boltzmann's constant, 1.38 times 10 to the minus 23, and temperature is 303 Kelvin. Therefore, plugging those numbers in, 1 times 10 to the 5 multiplied by 23.2 times 10 to the minus 3 divided by 1.38 times 10 to the minus 23 times by 303. And obviously we're expecting quite a large number because we're talking about numbers of molecules. I end up with 5.5483 times 10 to the 23, which if I put into appropriate number of significant figures, which again is 3 sig figs for this question, 5.55 times 10 to 23 molecules. Okay, so that's it for the ideal gas equation. On Wednesday, we'll look at the work done to cause the gas to expand or contract, and we'll also start looking at kinetic theory and pressure of an ideal gas, which will be all about deriving the equation for the ideal gas laws. Try and focus on some of the exam questions that I've given you. Remember to email me if you've got any questions, and remember that your write-up for calculating the specific heat capacity is due in by the end of today, so make sure that you email me that if you haven't done so already. Currently, I think I've only got 4 people who've emailed me, so that means that I've got at least 9 of you who need to send me that so far.